Okay, so now I want to start talking about how we would derive our heat diffusion equation with cylindrical coordinates. So to start off, I'm going to draw a cylinder. And we're going to have some flow moving in here from left to right. I'm going to draw out our x, y, and z coordinates. This is going to be x, y, and z. And for the sake of this example, we're going to say that this flow from left to right is in the z direction. That way, when we go to draw this out, we can simply just focus on x and y. So now I'm going to just draw out our x and y's. This is x and this is y. And we want to start drawing out a piece of the cylindrical shell. So we're going to have this arc right here. And we're going to have a line connecting from the origin to the edge. That's going to represent our radius. And we're going to move over some angle that we are going to put as d theta. If we extend these lines outwards, that is going to be some sort of addition to our radius that we're going to put as dr. We're going to have a direction pointing upwards. That is going to be representative of our z line. And this is a change in that. So this is going to be dz. And we want to start thinking about some sort of energy balance. So we're going to need a control volume. We're going to add another layer to our shell. So this is the outer layer. And this shaded region inside here is the control volume. So we're going to need to draw this in 3D form. So I'm going to try my best to kind of map that out for you. It's a little hard to see, but you can kind of picture this as being a portion of our shell of our cylinder. So now we want to start thinking about our energy storage term, which we said previously is the density times the heat capacity times the volume times the temperature. And our differential volume in this case is going to be this arc length right here, which is going to be r times d theta times our other differential terms dr and dz. Now, if we want to make this a rate of change of energy storage, this is going to be the density times the heat capacity times the change in temperature with respect to time multiplied by our differential volume, which we said is r d theta dr dz. For our energy generation term, once again, this is a rate per volume. So this is going to be this heat flow Q dot per volume multiplied by our differential volume, which is going to be R d theta dr dz. And as we said previously, our rate of change of energy storage term is equal to the rate of change of energy generation plus the net heat flow. And we're going to have heat flowing in 3 different directions. We're going to have the z direction, a radial direction, and an angular direction. So let's start by evaluating our net heat flow in the z direction. And what that looks like is heat flowing through the bottom of this and out through the top of the shell. So we're going to have heat flowing in from the bottom, which is going to be QZ, and heat flowing out through the top at a different position, which is going to be QZ plus DZ. We have to take into account that later Z position that we are at. So this is going to be the heat flowing in minus the heat leaving. So QZ, our heat flowing in, minus QZ plus DZ, the heat flowing out. And we can represent QZ plus DZ using Taylor series approximation. So if we do that, that comes out to be the heat flowing in the Z direction plus the derivative of the heat flowing in the Z direction with respect to the Z direction multiplied by dZ. If we take this and plug this in right here, we end up with negative the derivative of the heat flowing in the Z direction with respect to the Z direction multiplied by dZ. We have this QZ term that we can actually relate to Fourier's law. So if we remember, Fourier's law is the negative thermal conductivity multiplied by the area multiplied by the change temperature, and in this case with respect to the, Z position. So now we can plug this back in and we have the negative, the differential in the Z direction, multiplied by the negative thermal conductivity, multiplied by the area, multiplied by the change in temperature with respect to the Z position, times dZ. Our area in this case is going to be represented by this arc length, r d theta, times dr. So our area is r d theta dr. And if you'll note here, none of this is dependent on z, so we can actually take all of that out of our derivative. So simplifying that, we're going to have the net heat flow in our z direction as the differential in the z direction multiplied by the thermal conductivity multiplied by the change in temperature with respect to the z position times, if you'll notice we multiply these together, that is our differential volume. So this is multiplied by r d theta dr dz. And I'm going to highlight that as we are going to need that in a little bit. All right, now we can focus on a different direction, and we're going to focus now on our radial direction. So with our radial direction, we're going to have heat flowing through this side and leaving this side. So we're going to have heat flowing QR, and then a heat flowing at a later point, which we're going to have to note as QR plus dr, just kind of how we did last time with our z direction. So the net heat flow in the radial direction is going to be equal to the heat entering QR minus the heat leaving QR plus dr. Once again, we can represent this using Taylor series approximations. So we're going to have QR plus dr is equal to the heat flowing QR plus the derivative of the heat flow in the radial direction with respect to our radial direction times dr. Plugging this in, we are going to find that this is similarly the negative derivative of the heat flow in our radial direction with respect to the radial direction times dr. We can again plug in Fourier's law, which this time is the negative thermal conductivity multiplied by the area multiplied by the change in temperature with respect to r. Our area now is going to be r d theta, and this time multiplied by dz. So this is going to be r d theta dz. So if we plug this in, we're going to have negative the differential with respect to our radial position times the negative thermal conductivity times r d theta dz times the derivative of our temperature with respect to r times dr. Notice this time we cannot take out this entire area term because obviously this radius term is going to be needed in this derivative as it's dependent on r. But we can take out d theta and dz. So we're going to have the net heat flow in our radial direction is equal to the differential in the radial position multiplied by the thermal conductivity times r times our change in temperature with respect to r multiplied by d theta dr dz. And we are also going to highlight this as we will be coming back to it in just a second. Lastly, we can think about our angular direction. So we're going to have heat flowing through this side and out through this side. So this heat flowing in is going to be represented by q theta, and this heat flowing out at this later point is going to be q theta plus d theta. So our net heat flow in our angular direction is going to be the heat flowing in q theta minus the heat leaving q theta plus d theta. Again, using Taylor series approximations, q theta plus d theta becomes the heat flow at theta plus the derivative of the heat flow at theta with respect to theta times d theta. If we plug this in, we will find that this is similarly negative the derivative q theta with respect to theta times d theta. Once again, our Fourier's law equation is going to be the negative thermal conductivity multiplied by the area multiplied by the change in temperature with respect to theta. Our area in this case ends up being dr times dz. So plugging this in, we're going to find that we'll have negative the differential with respect to theta multiplied by negative the thermal conductivity times dr dz times the change in temperature with respect to theta multiplied by d theta. This eventually becomes the net heat flow of theta, which is equal to 1 over r d over d theta multiplied by our thermal conductivity times the change in temperature with respect to theta multiplied by dr d theta dz. All right, now that we have all three of our net heat flows, we can assemble our original equation. The rate of change of energy storage is equal to the rate of change of energy generation plus our net heat flows. So just as we said before, the rate of change of energy storage is going to be equal to the density times the heat capacity times the change in temperature with respect to time, multiplied by our differential volume, which we said is R d theta dr dz. And this is equal to all of our heat flows, our net heat flows that we found. So starting off with the z direction, we had the differential in the z direction multiplied by k times the change in temperature with respect to our z position multiplied by r d theta dr dz. Next, in our radial direction, we had the derivative with respect to our radius multiplied by our thermal conductivity times our radius times our change in temperature with respect to our radius multiplied by d theta, dr, and dz. Finally, for our angular direction, this was 1 over our radius times the differential in our angular direction multiplied by our thermal conductivity multiplied by the change in temperature with respect to theta times dr d theta dz. And of course, we can't forget about the addition of our energy generation term, which was the heat flow per volume, Q dot, multiplied by our differential volume, R d theta dr dz. Now, if we want to isolate this change in temperature with respect to time, we can first start off by dividing by our differential volume. So we can divide this out and divide this out. And once again, we need to take out an r, so we're going to be left with the 1 over r over here. We can cancel this. Once again, we're going to need to divide by an r, so this becomes r squared, and this cancels as well. To make our life easier, we can say that these thermal conductivities do not change whether or not we're in the z direction, the angular direction, or the radial direction. So we can take all of those out of the derivatives and divide by our density times our heat capacity. Because as we remember, thermal conductivity divided by density and heat capacity is thermal diffusivity, or alpha. So simplifying this, we're going to have the derivative of our temperature with respect to time is equal to our alpha, our thermal diffusivity, multiplied by the second derivative of temperature with respect to our z position, plus 1 over r times our differential of r times the change in temperature with respect to r, plus 1 over r squared times the second derivative of temperature with respect to our angular direction theta, plus our energy generation term Q dot divided by our density and our heat capacity. And now we can say that this becomes our heat diffusion equation for cylindrical coordinates. Now I want to take our same heat diffusion equation we derived for cylindrical coordinates, and this time I want to take an example where we're at steady state, there's no energy generation, and heat is flowing only in our radial direction. So to do this, I'm going to take us all the way back to our coffee cup example, except this time we're going to have some sort of thickness that we can't just simply ignore. So within the shell of our coffee cup, we're going to have some sort of inner radius that we're going to say is Ri. as well as an outer radius of RO. And each of these have their respective temperatures, an inner temperature and an outer temperature. Now, simplifying our equation based on our conditions, our equation becomes 0 is equal to R, our radius, times the change in temperature with respect to our radius. And this is equal to a constant, so we can actually change our equation to look like R times the change in temperature with respect to our radius is equal to some constant we'll say is C1. Now this becomes a separable differential equation. So we can separate our terms to have dt on the left, which is equal to our constant C1 divided by some radius r with respect to our radius. Now we can integrate these, and let's integrate from our inner temperature to our outer temperature and our inner radius to our outer radius. Solving these integrals, we're going to have the outer temperature minus the inner temperature is equal to our constant C1 times the natural log of our outer radius divided by our inner radius. Solving for C1, we're going to have C1 is equal to the outer temperature minus the inner temperature divided by the natural log of the outer radius divided by the inner radius. Now we can do this integration as well if we wanted to, instead of going from our inner radius to our outer radius, we go from our inner radius to some point in between. So we can have our same integral setup, except this time we're going to evaluate from some inner temperature and some inner radius to some radius and some temperature. And we're going to have to use dummy variables of integration so that we don't get this r confused with this r and this t confused with this t. So to do that, we're going to add in our dummy variable of integration, and now we can simply solve. So this becomes some temperature T minus the inner temperature is equal to C1, our constant, times the natural log of our radius at some point divided by our inner radius. Now this is analogous to what we said before about resistances. So just like we said before, in electrical circuits, we have a change in voltage, delta V is equal to our current times our resistance. And we said this was analogous to a change in temperature, which is our driving force, which is equal to our heat flow Q multiplied by some thermal resistance. We know that Q can be solved using Fourier's law, which is the negative thermal conductivity multiplied by the area multiplied by the change in temperature with respect to our radius. Our area term is going to be 2 pi times our radius. We can choose either the inner or the outer radius. For this example, I'm going to choose the outer radius times some height. And for the sake of this example, I'm going to make the height 1 meter. Therefore, we can kind of just take it out of our equation. Just note that it is there. It is just simply 1 meter. So now plugging this back in for Q, we have Q is equal to negative 2 pi K times our outer radius times our change in temperature with respect to our radius. To find this term right here, we're going to go back up to this equation that we had found, and we're going to move our inner temperature over to the right side. So this is going to be T is equal to our inner temperature plus C1 times the natural log of the radius at some point r divided by our inner radius. Now we're going to take the derivative with respect to our radius, so this becomes dt over dr. Our inner temperature cancels out, and then this is equal to C1 times R I over R multiplied by 1 over the inner radius. Now we can see that our inner radius terms cancel, and we are left with dt over dr is equal to c1 over some radius r. And we used our outer radius for our area, so I'm also going to evaluate this as at our outer radius just to stay consistent. So this is now our constant C1 divided by our outer radius. So now we can take this and plug it in down here. So we're going to have Q is equal to negative 2 pi times our thermal conductivity multiplied by our outer radius multiplied by our constant C1 divided by our outer radius. As you can see, our outer radius terms cancel, and we're left with Q is equal to negative 2 pi times our thermal conductivity multiplied by C1. Well, we already solved C1 up here, so now we can plug that in. Q is equal to negative 2 pi times our thermal conductivity multiplied by the outer temperature minus the inner temperature divided by the natural log of our outer radius divided by our inner radius. As you can see, this now becomes a form of delta T. This is our temperature change, our driving force. So now we can simplify this to be our heat flow Q is equal to negative 2 pi times our thermal conductivity multiplied by delta T over natural log of our outer radius divided by our inner radius. Now we can simply rearrange our terms so that we can have our equation in this form. So this is going to be delta T is equal to Q multiplied by the natural log of the outer radius divided by the inner radius all over 2 pi k. And that is how you solve the heat diffusion equation for cylindrical coordinates if you are at steady state with no energy generation and heat flowing only in the radial direction.